All right, so the first thing I want to look at is our increasing decreasing tests. There's actually no new, we've been using this increasing decreasing test actually since I introduced the derivative. But we haven't formally spelled it out, so now we're going to do so. So what it says is that if f prime of x is greater than 0 for all x in AB, then f is increasing on that interval. And I don't think there's a whole lot new there. Does that make sense? So what am I saying? If the derivative is positive, well, if the derivative is positive, what are we saying about the slopes of the tangent lines? They're all positive, right? So if the function has positive tangent lines over some interval between a and b, then the graph would have to look like this, right? Something like that, where you have positive tangent lines. So what's that function doing? It's increasing over that interval. Okay? So I think you could actually, in fact, why don't you go ahead, fill out the second one. Okay? Take a guess what you think that is. Check with your neighbor. You got Steve lecturing tonight. It's great. It's great. Okay, so I think if we just switch that around, if f prime of x is less than 0 for all x contained in AB, then f is what? Decreasing. Then f is decreasing. On AB. So I said we've had this, we've been using this all along. Well, why did we wait till now to put it in a formal statement? Well, one, you're just building some intuition, so sometimes it's nice to hold off on the formal statements, but it's actually the proof of it that's actually complicated, proving this. So let's go ahead and do so. So I've got a statement about the function's derivative, and I've got a statement about values within the function. What could I do to connect those two ideas together? What should I use? You're right. The mean value theorem, right? We're going to use the mean value theorem to prove it, okay? Which is often the answer in these calculus questions, okay? So let's see what we can do here, okay? Let's pick two x1. Let's pick two x values. Let's pick x1 and x2 be in that interval AB. So we're picking two arbitrary x values in that, okay? And let's just say. We need an order to them, so let's just say x1 is to the left of x2. So these x1 and x2 values are arbitrary. I just picked them out of a hat, and I'm just ordering them. I'm putting one to the left, one to the right, as it goes. So by the mean value theorem, so first of all, I'm about to use the mean value theorem, can I?
If it's continuous and differentiable.
So continuous on the closed bounded interval and differentiable on the interior. Well, here's the idea. The derivative, I'm just proving A, just part A is the only one we'll prove, and part B is similar. But we'll just prove part A. So I'm saying that the derivative is positive for all x in the interval A to B, right? Well, then that means it's differentiable on A to B. And if I pick a x1 and x2 inside of there, I can now build a closed bounded interval on there. So in fact, let's go ahead and spell that out. For the interval x1 comma x2, there's going to exist a c value. So that will be my closed bounded interval, the x1 and x2 that I chose. Okay? And certainly it's differentiable on the interior of that because it's differentiable on AB. And it's continuous because differentiability does imply continuity. Now be careful. It's not the other way around. Continuity does not imply differentiability. Think of your absolute value function. Okay? But the mean value theorem then applies here. And so what's the conclusion of the mean value theorem? It's been a week. If you've got a continuous function on a closed bounded interval that's differentiable on the interior. Yeah? What's that? There exists a C value. Okay. There exists a C value contained in, so in this case the C value is not going to be in AB. We're going to write it in the interval x1 comma x2. So that what?
F of C equals F of B minus F of A over B minus A.
Close, not quite F of C, but F prime of C. Exactly. So I'm going to state, that's exactly right. I'm going to state the mean value theorem another way. I'm going to write it as the alternate version. So if you remember when we gave it, we had two different versions. So I'm going to say f of x2 minus f of x1 is equal to f prime of C times x minus x1. But notice if I divided this over, I'd have exactly what Taylor said. Okay. And just to help you remember, if I had divided this, oops, I'm sorry, that's a mistake here. That should be x2 minus x1. If I had divided that x2 minus x1 over, then what would I have? I'd have an expression that says the average velocity equals the instantaneous. So remember, that's how you remember the mean value theorem. There's a place where the average, or there's a place where the instantaneous equals the average. Okay? But here's what's going to make this argument work. Okay? What do we know about this expression right here? Well, we know that x2 is bigger than x1. So what does this difference come out to be? What type of number? Positive number. And in part A, what are we assuming that the derivative always is? Positive. What is the product of two positive numbers? Positive. So what do we say about this whole expression? We know it's greater than 0. Okay? So then we know that f of x2 minus f of x1 has to be greater than 0. And now let's just solve the inequality. Then we know that f of x2 must be greater than f of x1, which is the definition of being increasing. Pick two x values. Show that the leftmost one has a y value that is below the y value of the rightmost one. And that's what we've just shown. It's kind of a slick little proof. Really give yourself a little box. All right. So how are we going to put this increasing decreasing test into action? Well, to be honest, I usually won't ask a problem that is that straightforward. Tell me where this function is increasing. That'll be taken into account in larger problems. But let's go ahead and say, for this problem here, we want to know for which intervals is the function increasing and for which intervals is the function decreasing. Okay? So this is sort of the roadmap that I want you to follow. There's other ways to arrive at the answer, but I feel like this is the best way, knowing what's coming up when we get to section 4.4 with our graphing techniques. So this is the way I would prefer you to do it. So what? Well, first find the critical numbers. Okay, so how do we find critical numbers? Well, what are critical numbers? I forget. It's been a spring break.
It's where the derivative is 0 or undefined.
All right, so there's two options to be a critical number. Either it's where the derivative is 0, no one ever forgets that one, or where the derivative is undefined, and half the students always forget that one. Okay, so don't forget, there's those two requirements, or not two requirements. There's two options to being a critical number, where the derivative is 0 or where it doesn't exist. Well, let's go ahead and find critical numbers, so we better take the derivative. So we get 12x cubed minus 12x squared minus 24x. Okay, let's see here. I think we factor out a 12x, and when we do so, we get x squared minus x minus 2. So I think we could keep going. X minus 2, x plus 1. Folks, if you're rusty on factoring, well, unrustify yourself. Do some practicing, because factoring is going to show up pretty heavily in this at least the first two sections of this unit. Okay? And it would be a real bummer to know the calculus and to get stuck on the factoring. All right. So we've got critical numbers from two locations where f prime of x equals 0. Where does that happen? That happens if x equals 0, or if x equals 2, or if x equals -1. Where else could we possibly have critical numbers?
Where it's undefined, but since it's a polynomial, it's continuously defined.
Exactly. So we could ask the question, where does f prime of x not exist? But as Karina just said, it's a polynomial. So its derivative exists everywhere, so there are none. Okay? So I always put this up here, or I'm going to try to always put this up here. Oftentimes, for these simple examples we give, this part doesn't apply, but it's critical in some examples. So I'm just trying to reiterate it. All right. So this is the next technique. Okay? And this is the technique that's going to carry over going forward. Okay? So you're going to build a number line. Okay, what are we going to do with this number line? Well, we're going to build a number line, and on the number line, we are going to put all the critical numbers of the first derivative. So let's see here. We've got -1, we've got 0, we've got 2. What have I just done? I've taken the number line and I've broken it up, in this case, into 4 regions, separated by the critical numbers. Okay? I claim that the sign of the derivative cannot change within any one of these intervals. That if I put in a number here and the derivative comes out to be positive, then if I plug in this number here, the derivative has to stay positive. Why is that true?
Because we've already defined with the critical numbers that those are the points where the graph is changing.
Everyone hear what Karina said? I agree with that. Okay? So we've listed, I mean, if you think of the first derivative as a function, okay, let me just kind of come over here, sketch. How could a derivative jump from, say, this positive region here to this negative region here? It could do it one of two ways. It could either go down, in which case it crosses the axis, in which case the derivative was 0 someplace, in which case we would have picked it up in this category. Or, how else could it possibly get down there? It could do something like this. It could just jump. But if it jumped, it was what? Undefined there. Okay? By the way, we've never said this. You would never have, in the instance of finding a derivative, something like this. Okay? You would never have that happen in the instance of finding a derivative. So, yeah, okay. So, if it were to jump like that, what would you have? Well, you've got a discontinuity of the first derivative, which we would have picked up in this column right here. Okay? So that's why you do need both in order for this process to actually work. Okay? All right. So now that we've built the number line, we've put the critical numbers, I claim that all we have to do is examine one point's behavior in each of these intervals. Okay? So we're going to take what I call test points. Okay? By the way, this should seem strikingly familiar to a technique we did on the very first exam. It had nothing to do with calculus. It was just a domain question, but this building a number line and evaluating points within regions is this same idea. So let's pick some test points. I'm thinking of a number to the left of -1. What are you thinking of? I like -2, personally, but if you put in -3, you're fine. Okay? I'm thinking of a number between -1 and 0. How about -0.5? Between 0 and 2. Okay, what number are you thinking of this to the right of 2? To the right of 2. That's right. 750. I'm going to go with 3. All right. So what do we do now? Well, we've picked our test points. I would argue that after just a few days of picking test points, we all end up just picking the same ones. But it does not matter what number you pick, okay? Because of the way we've developed this number line chart. Now what are we going to do? Well, it's enough now to just identify what is the derivative for each one of these test points. So we're going to find f prime of the test point. Please, 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 folks, be very careful to annotate stuff and annotate it correctly. I know you know how big of a difference that prime mark makes, but we're not plugging it into the function, we're plugging into the function's first derivative. How come? Because I want to use the increasing-decreasing test that we just talked about. And the increasing-decreasing test talks about the sign on the derivative. Okay, so now I'm going to plug each of these test points into the derivative. I'm not actually concerned with what number pops out. All I'm concerned about is the sign on the derivative, the SIGN on the derivative. Okay, so let's see here. Let's plug -2 into the derivative. Well, I could plug it into this original form of the derivative, but it makes a lot more sense. It's faster to evaluate if you plug it into the factored form. Okay? So when I plug a -2 into this first factor right here, what's the sign on that first factor? Negative. When I plug in a -2 into this factor here, what's the sign on it? Negative. If I plug in a -2 into this factor here, what's the sign on it? Negative. What is the product of a negative times a negative times a negative? It is negative. So what I'd like you to put, though, is I'd like you to put some pictorial representation of what it means to have a negative first derivative with regards to the original function. Well, if the first derivative is negative, what does that tell us about the function? It is decreasing. So what I'd like you to do is put a little down arrow like that for decreasing. Okay, you could put a negative sign there, but I think you're in better shape if you put the down arrow. Okay, we plug in -1/2. Well, that's negative, but that's now positive. So we're increasing. We plug in 1. That's positive, that's a negative, that's positive. Product of those three is negative. And we plug in 3, and we get positive, 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 so it's increasing. Will I ever get 0? No. Will I ever get undefined? No, because the only places where that could happen showed up here. Folks, do make sure you really delineate your regions. It's very easy to, as you write this out, start plugging in your critical numbers into your first derivative, which doesn't help you. Okay? All right. So I think now we can answer the question. F is decreasing on the interval from -infinity to, so this whole region here, right? This test point was arbitrary. I could have picked -750. Okay. For any test point between -infinity and this critical number here, the function is decreasing. Okay. It is also decreasing from 0 to 2. Okay. All right. I do need to make a quick comment here that I didn't make in my other class, and I probably should have. If you use the increasing-decreasing test, this is in the video so people see it. Let me just put this in a page here. If you say that f is decreasing on, say, -infinity to -2, unioned with -2 to, say, 7, okay, and the function is defined, and f prime of -2 exists, if it's differentiable there, so it might be 0 there. Okay, specifically, that's the case where this would happen. If the derivative was 0 at -2 and it was decreasing before -2 and decreasing after, and somebody's asking you where's the function decreasing, you would say it's decreasing on -infinity to 7. Does that make sense? You have to put those. You should put those two intervals together because it's also decreasing at 0. So a function could be decreasing at, you could have to include 1 point, even though the derivative test didn't help, the increasing-decreasing test didn't help you at that 1 point. Does that make sense?
So what's happening at that?
Yeah, that's a really good question. We're going to explore that as we go. But here, let me give you, so we're going to explore that. We'll give a name to it in just a second here. But if you wanted a picture of what might cause that to happen, maybe something like that. So it's certainly decreasing before C, it's certainly decreasing after C, At c, the derivative is 0, but if I asked you where is this function decreasing, you would say everywhere. All right. Great. So it's decreasing, and then where is f? You go ahead and list where f is increasing. Yeah. What's that? Yep. Yeah. Sorry. Yep. So increasing from -1 to 0 and to infinity. Any questions on that, folks? Okay, I'm just going to do the one example of that. We're going to incorporate this really into some larger tests that we're about to be doing. Okay? All right. Okay. I've always found this part a little bit confusing. We are going to teach two different derivative tests. One for the first derivative and one for the second derivative. Okay? So we call them first derivative test and second derivative test, respectively. In a lot of cases, you may use either test. Okay? But in some cases, one of the tests may not apply. Okay? So oftentimes you have an option, but we're going to give you both of these tests, and they both have their importance. Okay? So I can see that causing, well, which one should I use? Well, a lot of times it won't matter. It turns out that, in my opinion, the first derivative test is a little bit more work, but it tells you more about the graph. The second derivative test is oftentimes easier to do, although not always, depends on how hard it is to compute the second derivative. Is oftentimes easier to do, but you're left with very localized information, and you don't get that nice chart that we were just working on. Okay? So a lot of times for very specific problems, I'll use the second derivative test to check things, but if I'm building a graph, I'll use the first derivative test to talk about local maxes and local mins. Okay? So that's a little bit confusing. Okay? You've got two different tests. Oftentimes both apply. Sometimes only one applies. We'll try to ferret that out a little bit, but keep that in mind as we go forward. All right, so we've got the first derivative test. Suppose c is a critical number of a continuous function f, and f is differentiable near x equals c. Okay. Then what? Well, if f prime changes sign from positive to negative at x equals c, then f has a local max at x equals c. I think we've been building up to this. If you remember, I mean, we've done Fermat's theorem, which was related to this, and a couple of the other things we were working on as we were developing the mean value theorem, sort of reminiscent of this. Does that make sense? So what are we saying happens at c? At c, f changes from increasing to decreasing. If the function exists there, then it's got a local maximum there. Okay. Likewise, if f changes sign, or excuse me, if f prime changes sign from negative to positive at x equals c, then f has a local min at x equals c. Questions on that, folks? This test is a little bit more powerful than the second derivative test because if it doesn't change signs, we can still make it, we can make a conclusion. It's not a very exciting conclusion, but we can still make a conclusion. Okay? So in a lot of cases in math, we'll give you a test, and there might be, in case 1 it does this, in case 2 it does this. If you meet case 3, then the test fails. You can't do anything with the test. But actually, this is a little bit more. This is a little bit stronger than the second derivative test that we'll show in a little bit. And it says if f prime doesn't change sign, on either side of x equals c, then f has no max or min there, either a local max nor a local min. A lot of writing. Need to go back and fill those in as partial notes. Okay. So the pictures that go with this, I think, really help to clarify. Here's c, and we're saying that before we get to c, the function has a positive derivative. Well, if the function has a positive derivative, what's it doing? It's increasing. And we say after we leave c, the function has a negative derivative, so it's decreasing. Now, it doesn't actually matter, as long as the function exists at c, it doesn't matter whether I've got a cusp or a horizontal tangent line or a corner. In all cases, what have I got? I've got a local max there. Okay? So one scenario would be this one here. Certainly we have a local max at x equals c. But another scenario might be something like this. We might have the functions increasing before we get to c, the functions decreasing after we leave c. The derivative doesn't exist at c, but we still have a local max. Remember, I didn't say that the derivative had to exist at c. I just said it had to be a critical number. So it's either 0 or doesn't exist. Okay. So the other pictures are very similar. So we might have this scenario here where the function's decreasing before we get to c, and it's increasing after we leave c. Okay. If the derivative exists there, then by somebody's theorem, Fermat's theorem, we've got to have a horizontal tangent line. Okay. But even if the derivative doesn't exist there, say we have a sharp corner, even if the derivative doesn't exist there, we still have a local min. Okay. It takes into account both possibilities. Or all three possibilities, I should say. Okay. Now, the other instance is, well, maybe the function is increasing before we get to c and continues increasing after we leave c. Well, from this graph, you see that this graph has no local max or min at c. And what the theorem is telling us is that's not unique to the picture I just drew. That would always be the case. There's no way it could change, it could not change and have a local max there. Now there is one other case we could consider. Let's see if I can do it. Let's do this one here, just for fun. So at c, again, the function's decreasing before it gets to c. It's decreasing after it leaves c because the derivative is negative before c and the derivative is negative after c. It's not differentiable at c in this case. But it's still, there's no way it could give rise to a local max or a local min. Any questions on that? Okay. So a proof doesn't, or pictures don't justify a proof. Okay. Rather, I'm just giving you these pictures to sort of get a warm fuzzy about this. Okay. Actually, the proof for this is just a combination of Fermat's theorem and the increasing-decreasing test that we just did. All right. So here we're asked to, number 4, find the local maximum and local minimum values. This is not a question that I asked you on your last exam. What did I ask you to do on your last exam? No? I heard it? We found the absolute or the global maximums and minimums on the last exam. Okay, we didn't yet have the increasing-decreasing test, so we could not find local maxes and mins. Okay? So, I mean, we talked about them. I asked you questions about them, and we discussed them, but we didn't actually say find the local maxes or mins. Okay? All right. So now let's actually do that. So here are our steps. Step 1 is to find the critical numbers. How are we going to do that? What do I have to do first? I have to find the derivative. All right. F prime of x is equal to 12x squared, 6x minus 6. Put it in factored form. So let's see, 6 is 2x. Shows a little more room. 2x and x, and let's see here, it'll be 1. We need a 1 here with a plus sign and a minus 1 here. Everyone factors their own way. I didn't have office hours today. I'm sorry, folks. I forgot I had to go to another campus for an observation. But I've got office hours tomorrow, Wednesday, and Thursday, and it's just after a test, which means I am not very busy during office hours. If you want to talk about factoring, we can talk about factoring for a little bit. Okay. All right. So we found the critical, well, we haven't quite. What are our critical numbers? They're at x equals 1/2 and at x equals -1. Okay. Where did both those critical numbers arise from? They arose from the zeros of the first derivative. In this case, the first derivative, though, was everywhere defined. So I'm always checking that. All right, so we found the critical numbers. Okay. Step 2 is to go ahead and build that number line just like before. So we build a number line onto our number line. We're going to put all of our critical numbers, only 2 in this case. I'm thinking of a number to the left of -1. I agree. Between the 2, to the right. Okay? So these were my test points. What do I do now? Plug them into the derivative. Okay? So what is f prime of -2? So the derivative's positive, so it's increasing. Notice I didn't actually plug -2 into the function and compute it. I just looked at its sign. Nothing wrong with computing it, it just takes a little bit more time. Okay? Then we plug in 0. We get that it's decreasing there. We plug in 1 and it's increasing there. Okay? So I didn't ask you for the intervals for which it's increasing or decreasing. I could. But in this question, we're asked to find the local extrema. What did we just show? We just showed that at, so let's spell it out. At x equals -1, f prime changes from positive to negative. So what have we just shown?
You have a maximum here.
A maximum for whom? At -1, we'll have a maximum for which object? For the original function f, right? So f has a local max, as Kevin said, at x equals -1. Okay. Similarly, f has a local min at x equals 1/2. One reason why I like to do these arrows, folks, is these arrows actually let me get a sort of, I mean, it's not a very good visualization, but a decent visualization of what the graph's going to look like. And I think you can actually see the fact that there's a local max at -1. And you can see the fact that there's a local min at 1/2. Yes?
So for the previous problem, when we did the test points,
Uh-huh.
because it goes decreases, increases, decreases, increases,
Yes.
then you have to plug in the critical numbers to determine which one is the actual local min, since there's like 2 times that.
Yeah, so we never finished that question, right? So in the last question, I was just asking you for the intervals, but we could have answered the full question here and said there's a local min at x equals -1, and there's a local min at x equals 2. There's a local max at x equals 0. Now be careful. These are all local statements. They're not global. I'm not asking the question, what is the global minimum here?
So
Certainly our 2 candidates for global min are right here and right here because I have no endpoints. And I don't know, one of them would be the global min. Maybe both. But I'm not asking that in this question. That was the last test question, and we're going to put the two questions together here in the next example. But for right now, we're just asking the question, for the neighborhoods, where are the peaks and valleys, not what is the highest point on this function. Yeah, great question. Okay, look, I don't feel like we've actually answered the question yet. We've given the locations of the local maxes and mins. I'd actually like to find, first of all, the ordered pairs for the local maxes and mins. How am I going to do that? Plug them into where? Into the original function, right? What does the original function tell me? The actual height of those points. That's what I want, the ordered pair, right? So let's go ahead and evaluate f of -1 and f of 1/2. So if your name begins with an A through M, do the first one. If it's N through the end, do the second one. What do we get for the second one? I'm tired. Whoops. -3/4. That's what I thought. I don't know why I wasn't. All right, -3/4, and we got 6 for the -1. Okay. So what are the ordered pairs here? The ordered pairs, the points for the local maxes and mins are -1, 6. That's the ordered pair for that local maximum, and 1/2, -3/4. This is our max. Local max. This is a local min. Is there anything that says a function has to have a local max or a local min? No. Is there anything that says a function has to have a global max or global min? Not just at any state, right? There's nothing that says a function has to have a global max or a global min, unless I say that the function is, we're talking about it on a closed bounded interval. Then we're guaranteed to have both a local max and a local min. Okay? All right. So I think the question was for the actual values. So this would be the answer to the local maximum value. This would be the answer to a local minimum value. All right. So this question is a little bit different. It says find all extrema to this function f. How is this question different from the previous question?
It includes global, so you have to evaluate the endpoints of the interval.
Yeah. Everyone hear what Kareem said? So So when I say extrema, first of all, extrema just refers to the maximums and minimums collectively. But when I say all of them, I mean the local maxes and mins, if there are any, and the global maxes and mins, which there must be in this case, because we've got a closed bounded interval with a continuous function defined on it. So there's lots of ways you could go about doing this. If you look at your steps for finding local maxes and mins, or if you look at your steps for finding global maxes and mins, both of them involve first doing what? Finding the derivative with the intent of finding the critical numbers. So the first step for either of them is to find the critical numbers. So let's do that first. Okay. So let's find the critical numbers. So go ahead and do so. Take the first derivative, set it equal to 0, and solve for x. Talk with your neighbors. Yep. Go.
Wait, what'd you say? Oh, gosh.
First time I get a class that everyone knows the answer to that question. I'll retire. Really, I'll retire. How do we do that, folks? So first of all, we're not going to consider all possible angles where the cosine value is -1/2. There's a lot of them. I specifically want the angles in between 0 and 2 pi where the cosine is -1/2. If you are stuck, did you draw a tiny little circle on your page? Well, and you should. Draw a tiny little circle. Draw a tiny little circle on your page. Okay? Cosine on the unit circle refers to what coordinate? The x coordinate. Okay? Cosine on the unit circle refers to the x coordinate. We want the x coordinate to be -1/2. Where is that? That's right about here. So that would happen at this point or at this point. What are those two angles? All right. That happens when x is equal to 2 pi over 3 or 4 pi over 3. How do we do? A couple of you got it? Awesome. Okay. If you didn't, it takes some practice, okay? Spend a little. Notice, so remember I said to you guys when we introduced trigonometry, I said don't draw the whole unit circle every time you want to answer a question, but just draw a little bit of it. How did we get to this position? We went back a little, right? And up a lot. Well, what angle is that? That's a pi over 3 angle. It's not the first pi over 3, but it is the second pi over 3. It's certainly not the 3 pi over 3, which is down here at pi, but then it's the next pi over 3 at 4 pi over 3. Okay. All right. Where are we? We found the critical numbers. Good. Okay. I'd like to now go ahead and let's go ahead and find the local maxes and mins, if any exist. Okay. So for this, we just went through this process. We're going to make the number line. On the number line, I'm going to go ahead and just emphasize by adding a 0 here. 2 pi over 3. I guess I could put the 0 of 2 pi over 3, 4 pi over 3, and then we'll put a 2 pi over here. Okay. So I'm adding on the endpoints here. I really should, especially since I only classify critical numbers that are inside that interval, then when it comes to picking that test point, I need to make sure the test point is actually within these, for first and last test points, that they're actually within the intervals. Okay. You can sometimes pick the endpoints, but you really should just pick something that's interior to it. I'm kind of getting into trouble here because different authors use a different definition of what a critical point is. But anyway, let's pick our test points. What's the easiest angle to evaluate between 0 and 2 pi over 3? Well, if we don't plug in the endpoint, I think pi over 2 would be a good test point. We could do pi over 2. I think we could do pi. I think we do 3 pi over 2. Okay. So what are we going to do? We're going to plug them into the first derivative. Okay. We're going to look at the SIGN, the SINE. Okay. So we plug in pi over 2 into the first derivative. Well, you guys do it. You fill out the chart. So I think that we got that the first derivative was positive for the first interval, negative for the second, and positive again to the third. Any questions on that? Okay. So it seems to me that we've got a local max at x equals 2 pi over 3 and a local min at x equals 4 pi over 3. Any questions on that? Okay. So the next step is to actually find, well, so we found the local maxes and mins, and that's a great question to have answered. We've got one more question to answer. What is it?
Global maximum.
Global maxes and mins. What are we going to do for that? Yeah, so that's a question of who's king of the hill all across the board, right? So we need to actually compare the y values for that. We're not saying, are you the tallest guy around, the tallest guy in your neighborhood. We're saying, are you the tallest in the whole earth of this problem, the whole universe of this problem. Okay? So we're going to look at, I'm going to find f of 0, I'm going to find f of 2 pi. I'm also going to find f of 2 pi over 3 and f of 4 pi over 3. Okay? I'll do the first one, that's 0. Actually, I'll do the second one, that's approximately 6.28. If you would give me decimal approximations on the next two. So, this half the room, if you would do 2 pi over 3, this half the room, if you would do 4 pi over 3, if you do the wrong one, you'll be okay. Check with your neighbor though. So this half the room, what'd you get for f of 2 pi over 3? Oh, heard a lot of different stuff. Check with your neighbor. Check with your neighbor. Hey, how about this right hand side of the room? What do we get? What's that? No. No. 2.457? That sounds about right. Do I have a consensus on that? No? I don't know, 2.457? Okay. Call it 2.45746. Okay. This half the room, you guys get your story straight? 3.83 I'm hearing? Great. Okay. So, what's our global max? We have the global max at 2 pi. This is our global max. Oh, I can't abbreviate with an M. Global max. Okay. Where's our global min? There's our global min right there at x equals 0. Okay. By the way, you can now plot these points. As you can see, I've already given you the graph. I hope that didn't color your impressions of what it should be. But it is always nice to confirm this with a graph. Okay, we did not rely on this graph at all. All right. These questions. So this is an exam question, right? This is an exam question. This is a final exam question. Here's a function on an interval. Give me all of its maxes and mins. Okay. Where does this get harder? Well, it may be harder to take the derivatives. I mean, these weren't too hard to take the derivative of. You might have places where the first or second derivative is undefined, or excuse me, where the first derivative is undefined. That makes it a little more complicated. Okay. You have to make sure you're always checking. So notice, where else would I have critical numbers, or where else is the first derivative 0? Well, it's 0 again at add another 2 pi to that, so 6 pi, 8 pi over 3. The derivative would be 0, but I didn't include that because it was outside of my interval. So there were a lot of decisions we were making along the way here. Okay, you can't quite fly on autopilot for these questions. Okay, but anyway, that's the process. Okay. Okay. How are we doing on time? Yeah, let's keep going. All right. I would like you to go ahead and draw several tangent lines on each of these curves. at least 5 tangent lines on each of these curves. Okay, I couldn't fit 5 on there. I want you to notice there's something different about the first curve and the second curve. What is it? Very good. There's something almost more rudimentary than that. That's right. Then there's nothing wrong with that answer. In fact, it may be better than the answer I'm about to give. Well, not quite so rudimentary.
Intervals.
Top and bottom.
What's that?
Top and bottom.
So on the first graph, notice all the tangent lines are below the curve. And on the second graph, notice all the tangent lines are above the curve. There are different definitions for concavity. Different books give it different ways. I like the definition of concavity that says a function is concave up if the tangent lines are always below the curve on that interval. Okay? So this is a concave up shape. You need to somehow recognize this. And I find that by discussing tangent lines, it's a quick way for students who have never, many of you have never experienced concavity, which is wonderful, it's perfectly fine. If you've never experienced it, that idea of where are the tangent lines, I think is a very helpful idea for determining concavity. Okay? So, but however you're going to learn it, you need to know that this is a generic concave up shape. Okay, so everyone make a concave up shape. Okay? This is a generic concave up shape. Now, what's a little bit troubling, in fact, some of you mentioned this, what's a little bit troubling about a concave up shape is that it might just be doing that's concave up. Notice that the function is doing what? It's decreasing. Well, it's doing many things. It's decreasing and it's concave up. Right here, the function is increasing and it's concave up. So concavity has nothing to do with the instantaneous behavior of increasing or decreasing, or the localized behavior of increasing or decreasing. Okay. So you could be you've got to separate concavity from increasing, decreasing. Okay. Now, this generic shape right here is concave down. So if you ever want to know, this is a concave down shape, upside down parabola. That is concave down. Okay? Now again, you've got to be careful because a concave down shape might look like this. That's concave down. Similarly, this is concave down. In one instance, we're decreasing. In one instance, we're increasing. Okay? So, another way to talk about this, and this is what Tyler was saying, is to look and see that what are the tangent lines doing here? Not the function. What are the tangent lines doing? The tangent lines on the concave up interval, sometimes they're negative, sometimes they're positive, but as I go from left to right, they are increasing. It starts out negative, it's then a little less negative, it's then a little less negative, and then it hits 0, and then it's increasing. So I haven't decided what is the better definition, but the way our author defines it, our author says, hey, a function is concave up if the first derivative is increasing. Does that make sense? If the first derivative is increasing, what are the slopes of the tangent lines doing? They're increasing, which is precisely what we see in this diagram here.
So the first derivative increasing on a certain...
On an interval, yes. So these are all interval definitions on some interval I. So a function like this one right here for the interval that I've drawn it is neither concave up nor concave down because it starts off, for the first half of the interval, it's concave down. For the second half, it's concave up. Okay? Yeah?
Do you use an a value to a function? Like if it's positive or negative, determine its...
Yeah, so for a quadratic equation, yes, you could just simply look at the a value and determine that. But that's actually just a consequence of what we're about to see here. So that's not always going to be the case. So for example, if I have a 5th degree polynomial, some places it'll be concave up, some places will be concave down, and will have nothing to do with the actual sign on the leading coefficient. Yeah, it's a good question. It is true for quadratics, but it's not true for most other functions. Yeah. Okay, so I've given you that definition right here for concavity. Okay, here is another here's a third definition for concavity. This third definition is actually, I mean, they're all the same definition, because if the first derivative is increasing, we're going to say that it's concave up. But if the first derivative is increasing, then that means that its derivative must have what sign? Positive. What's its derivative called? What is the first derivative's derivative called? The second derivative. So another way to define concavity, and the kind of the quickest check that we'll ever do in this class, is if the second derivative is positive on an interval, then it's concave up on that interval. So the second derivative measures concavity. The immediate measurement, when you just plug a number into the second derivative, it tells you the concavity of the function. Okay? So if the second derivative is positive, it's concave up. When the second derivative is negative, it's concave downward. Yeah?
So wouldn't it be negative on that little section off to the left though, where it is still technically decreasing?
Which graph are we looking at?
For the up. For
This is concave up?
Yeah, so on just that little section to the left that's still decreasing, wouldn't you get a negative value for that?
Yeah, I would get a negative value for the derivative,
Mm-hmm.
but when I compare it to, so let's zoom in. Let's zoom in on it, if I can. Yeah. So there, yes, you're right. The first derivative is negative, but I'm not asking what the sign on the first derivative is.
Mm-hmm.
Just like when I give you a function, just f of x,
Right.
this function right here at c is increasing, and this function right here at c is increasing, and that has nothing to do with the sign, the height of the function,
Mm-hmm.
right? Okay. So I'm not asking a question about what is the first derivative when I'm talking about concavity, but rather I'm asking how is the first derivative changing? This had a slope of, say, m equals negative, say that's a slope of negative 2.
Mm-hmm.
Then what is this slope right here? Negative 1. What is the first derivative doing? It's increasing.
Gotcha.
So when the first derivative is increasing, we're concave up. Yeah, it's a great question.
I made a mess now. Oh boy.
There's no Zoom under tools.
All right. Hopefully you're okay. All right, the last thing we need to talk about is we have a name for where a function changes concavity. Okay? If a function changes from concave up to concave down, or from concave down to concave up at a point, and this is important for our text, if the if that second derivative is defined there, okay, then we're going to go ahead and say that there's an inflection point there. Okay? So, in fact, I need to add, this is again for a different book, so I need to change this to see here. Let P be a point on the function we call f, and on the function f. And suppose at least, we need to say at least f prime of P exists. Because our book doesn't allow for inflection points. Is that true? I'll have to get that. We'll see. All right. Anyway, if it changes concavity at a point, we're going to call it an inflection point. Okay? We don't have, so we had, if it changes from increasing to decreasing or decreasing to increasing, we had the terms local min, local max. We don't have, for inflection points, a word to mean going from concave up to concave down versus going from concave down to concave up. We don't have words for that. I don't know why, but we don't. We just call them both. Both those scenarios would be classified as inflection points. Okay? Any questions on that? All right.
Is there like specific verbiage or
No.
syntax to use?
No, so I guess I could still say, I could ask, give the location of an inflection point, but there's no word for the y value of the inflection point.
So like, but if you wanted to like say, like how it's changing at that point, you would just evaluate it before and after.
Yes, yeah, so by saying that there's an inflection point at, say, x equals 5, you don't know how the concavity is changing, you just know that it is changing there. And we don't have any, I mean, you could give more information, but we don't have any specific word that we're looking for. All right, let's go ahead and take a break. We'll come back here at the 45. We'll keep going. Okay, folks, let's pick it up. So, in this problem, we're going to just simply answer the question first, but then I want to show you, because eventually in the next, next time, we're going to get into graphing some complicated functions, so I'm just going to preview that a little bit. But we're given a function here, f of x is equal to x cubed minus 2x squared minus 15x, and we're asked, where is it increasing, where is it decreasing, where is it concave up, where is it concave down? Okay? So let's go ahead and answer those questions. So to do so, let's go ahead and start taking successive derivatives. Let's find f prime of x. This would be 3x squared minus 4x minus 15, which factors to be 3x and x and 3 and 5 and minus and plus. And if we take the second derivative, we get that the second derivative of this is 6x minus 4. Okay. Any questions on that? Okay.
Why are we taking the second derivative?
Yeah, great question. Why are we taking the second derivative? Well, just looking ahead at previewing the questions, we're asking where is it concave up and where is it concave down? And while we could ask the question where are the tangent lines above the curve or where are the tangent lines below the curve, we could also ask the question where is the derivative increasing, where is the derivative decreasing? The easiest way to answer where is the function concave up or where is it concave down is to say where is the first derivative positive, where is the second derivative, where is the second derivative positive, where is the second derivative negative. Yeah, so that's why. And sort of, I would just say that as we get going along, whenever it's a question that you think you're going to be graphing, you usually go ahead and plot both calculate both the first and second derivatives, just in anticipation of what will be coming. Okay, so now I'm going to identify the critical numbers of f prime. The critical numbers of f prime are at x equals negative 5/3 and at x equals 3. And let's go ahead and identify the critical numbers of f double prime. The places where, so here I'm thinking of f double prime as the derivative of the first derivative. And so that would be at x equals 2/3. So now what am I going to do? Well, I'd like to keep building on this chart that we've started. And this part is, different books do this differently, different instructors do this differently. I think this way is pretty common. There are some redundancies in the chart that we're going to make. So there's a little bit of, you're going to repeat some of the work unnecessarily, but I think you should make the chart this way. I think it's the best way to encapsulate some of the problems that you'll encounter. And yeah, sometimes you could have maybe saved yourself 1 or 2 calculations, but I think this is the best way to do it. So we're now going to make a number line, and on the number line, I'm going to put all of the critical numbers of both the first and second derivative. Okay? So we've got critical numbers at minus 5/3, at 2/3, that's a 5 there, and at 3. So now I'm going to go ahead and pick some test points. Let's see, negative 2 is my favorite number there. Maybe 0, maybe 1, and maybe 4. Okay. So now I'm going to evaluate all of these critical numbers in the first derivative, excuse me, all these interval test points in the first derivative to look for where the function is either increasing or decreasing. So we're going to go ahead and do that increasing decreasing test on it. Okay? Well, if I plug -2 into the first derivative, it looks to me like we would be, that can't be right. So see, that's negative and negative, so that'd be positive. So increasing, decreasing, increasing. Excuse me, I should actually slow down and actually do it. That's wrong. If you plug in 1 into the first derivative, this would be positive, this would be negative, so we're still negative, so that's decreasing. And if we plug in 4, we're positive, so that's increasing. It shouldn't really alarm you that between that for this interval and this interval, the derivative didn't change sign, because why was this critical number up here? It was a critical number corresponding to where the second derivative was either 0 or undefined. So again, there's nothing that says it can't change, but in this case, it definitely won't change because that's not why that critical number's up there.
So why did you put it there?
Why did I put it there? For what we're about to do. So yeah, so that was. So notice at this point, if I wanted to, we could pause. We could identify local maxes. We could identify local mins. Where it's increasing, where it's decreasing. But let's go ahead and keep going, and let's now plug that test point into the second derivative. Okay. And again, there is a little bit of, redundancy here. We don't actually have to check all these boxes, but you might as well just fill them all in, I think. Okay. So if I plug -2 into the second derivative, this would be 6 times -2 is -12 minus 4. Well, that's negative. So what does that tell us about the concavity of the function? We know that the function is concave down, right? So what are we going to put? We're going to put this generic concave down shape. Okay.
Wait, can you say what you said
Yeah,
one more time?
I think so. So we plugged -2 into the second derivative, and we got a negative number. If the second derivative is negative, that tells us the function is concave down. So rather than putting an arrow here, I put a generic concavity shape, concave down shape. Okay. Likewise, if I plug in 0 into the second derivative, it's still concave down. If I plug in 1, though, for 1, it would be concave up, and again for 4, it'd be concave up. So maybe you realize that there was a little bit of redundancy here, but it's okay. I don't think it was that difficult to evaluate those test points. Okay? By the way, if you wanted to be slick, you could, and if you want to get a real sense of what this graph is looking like, there is where the function would be both concave down and increasing. Here is where the function would be decreasing and concave down. Here's where the function would be decreasing but concave up. And so if you could sort of piece these parts together, and here would be increasing and concave up, and you could kind of piece that together to give you a sense of what the graph looks like. You don't have to do that. So let's just say it, even though the question none of the questions asked. We have local mins, or let's say local max first. Local max at x equals -5/3. Local min at x equals -3. Excuse me, +3. Thank you. And we have an inflection point where? At x equals 2/3. Why is that called an inflection point? So the function changed from concave down to concave up. It changed, the concavity changed sign. Okay? All right. So on which intervals is the function increasing? We can answer that. Up until -5/3. And again from 3 to infinity, I think. On which intervals is the function decreasing? Well, that would be on the inside of that. Where is the function concave up? It's concave up from 2/3 to infinity. And where is it concave down? It's concave down from minus 2/3, minus infinity to 2/3. Okay. How we doing, folks? Okay. We're not going to worry about completely how to graph f just yet, but I'd like to actually assemble it a little bit backwards. Let's start with graphing the second derivative first, because that's the easiest to graph, and we'll start getting a sense of how these all interplay. So the easiest function to graph here is the second derivative because it's linear. Okay, so we've already said it's got a 0 at 2/3. And its y-intercept is -4, and it's linear, so we put 2 points on there, so that's enough to sketch the graph of f double prime of x. Okay. Notice that, I mean, this shouldn't be too much of an aha, but where the second derivative is negative, the function is concave down, and where the second derivative is positive, the function will be concave up. All right. A little more interesting is graphing the first derivative. Okay, the first derivative had zeros at x equals -5/3, which is right -5/3, which is right about here, and at +3, which is right about here. It is a parabola. That's nice. We do know the y-intercept is -15. Okay. It has a vertex. Parabolas have vertices. We'll have a vertex. Where is the vertex of this parabola? At 2/3, because that's where its derivative changes sign. So that's where the original function, the original function referring to f prime, where f prime then must have a local max or min. Because at 2/3, f double prime changes from negative to positive, that means f prime must change from decreasing to increasing. So at 2/3, and if you plug 2/3 into the original function, or into the derivative, you get -16 1/3. So that's right about here. Well, it's right about here. Okay? So there's that point. And now we can go ahead and sketch this curve. Oh, that's pretty ugly. Oh well. Okay. Folks, I did something just a second ago that I think is a really important skill to build. Okay. I said the derivative's derivative changed sign at 2/3. That means that the derivative must have a local extrema there. Okay. That being able to talk about derivatives of derivatives is a difficult skill to acquire. Okay. You do need to spend some time on it. I did put up here this practice exam, and I want to point out one question on here. It's a long question. It has several parts. It's question number 7, and I say, suppose you're looking at the graph of f prime. Now answer some questions. Suppose you're looking at the graph of f. Now answer some questions. And that's a tricky skill to acquire. So do spend every day between now and the test working through this page. Okay? It will help develop your intuition immensely, I think. All right. So now we're back to the original function. By the way, we could have factored the original function. It would have factored as x times x minus 5 times x plus 3. So we can go ahead and put in the zeros at x equals 0, at minus 3, and at positive 5. Okay. What else do I know about this function? Well, I know that from minus infinity to minus 5/3, it's going to be increasing. Okay. And in fact, we said it has a local max at x equals minus 5/3. I plugged minus 5/3 into the function, and I got 14.8 approximately. So we've got a local maximum at minus 5/3, comma 14.8. That's right about here. We've got a local maximum. We've got a local minimum, we said, at x equals 3. Well, I plugged 3 into the function, and I got out negative 36. So at the order pair 3 comma negative 36, we've got a local minimum. Okay. So I think I've got enough to sketch this graph. Okay, so let's see here. Before we get to negative 5/3, we're increasing. At negative 5/3, we've got a horizontal tangent line. After we leave negative 5/3, we're decreasing. Okay, for this whole piece, I've got what sort of generic shape to this graph for this whole piece here? It is concave down, and it continues concave down until I get to x equals 2/3, where we've got the inflection point. I plug 2/3 into the function. And I got negative 10.6 approximately. So right about here, I've got my inflection point. And so what's it going to do at that inflection point? It's going to change from concave down to concave up. And there's the graph of this function. That's a pretty impressive thing to be able to do with very minimal calculations, I think. Granted, it's slightly cooked up. How is it cooked up? It was easy to factor. Okay, it does take a long time to find functions that, the function factors, its derivative factors, that's hard to do. I don't know what you guys spend it doing on your weekends, but.
This is a factored equation.
Oh, yes, yeah. Factored as x times x minus 5 times x plus 3. Yeah. So let's see. I mean, first of all, we said the function should be increasing on these intervals. Is it? Yeah. Until I get to negative 5/3, I'm increasing. After 3, I'm increasing. I was decreasing in between the two. It's supposed to be concave down before I get to 2/3 and concave up after I leave 2/3. But I think it's important to be able to see how much of that information you can get from any of these graphs. Okay? So you can only look sort of one level up with these graphs. And you can look 2 levels down with them. That's true as well. But notice, looking at the second derivative, I can't tell anything about where the original function's increasing or decreasing. I can tell that the function's derivative is decreasing for a while and then increasing. And we see that. The first derivative is decreasing for a while and then increasing. I can tell about the concavity of the original function. I know it's concave down until I get to 2/3, concave up after 2/3, so 2/3 is an inflection point. Okay. Right here, look at this function is decreasing until I get to 2/3. That means, so this is the longest leap I ever ask you to make, but it's a tough one, and I will ask you to make this leap. The derivative is decreasing until I get to 2/3, which means its derivative must be negative until I get to 2/3, which means the original function must be concave down until I get to 2/3. And that is a series of 3 jumps you got to make, and that's tough to do. Yes?
So for instance, without looking at the second derivative, we would still be able to determine concavity.
Yes, I can just so
Based
you
off
could
what you
have answered this. Yes, exactly. So if we didn't have this to look at, I could still say the function's derivative is decreasing. That's a statement about the function's derivative, about the second derivative. Yeah. So when you say that f prime is decreasing, you are describing f double prime. So you don't even have to look at it. And that's why I highly recommend you work on that exam review question right here, because it does sort of run the gauntlet of all possibilities you could see. Yeah. All right. Great.
So you said f prime of x is decreasing until 2/3, which means that f double prime of x is negative until 2/3. And because of those two, then that means it has to be concave take down.
The original function then would have to be, because, yes, yep. And you can see that leap through, you can see that through a lot of different, there's a lot of different lenses to use on that, yeah. Okay, folks, if you didn't get out of the habit of saying it's, as in the possessive pronoun, if you didn't get out of the habit of using the pronoun it's before, now you absolutely have to get rid of that pronoun. Because if you say it's increasing because it's positive, you won't know what you're saying, and I won't either. But you won't be able to keep track of things. If you say the function's derivative is positive, therefore the function is increasing, you'll be able to keep track of all of this. But as soon as you start saying the word it's, you'll lose yourself before and you'll lose me. So, okay. All right. Go ahead and give number 11 a shot. Yeah, we got time. If you are stuck, just draw something and fix it. But I mean, I'll be posted online here.
Yeah, no worries. It's not a big deal.
If I have any left over, that's fine.
I'll just pull a resentment on this for the rest of my life.
Check with your neighbors. Anyone not have a copy? Everyone have a copy?
Nice. Serendipitous.
All right, folks, you may not have gotten it yet, but let's pause here and let's make some statements, and then you can keep working on it. What is going on at x equals 1 from that first bullet? Well, before we get to 1, it's increasing. And after we leave 1, it's decreasing. So what's happening at 1? We've got a local max. Local max at x equals 1. Great. Okay? You see how you can get information from this, right? Which maybe you sort of recognize that, but I think if you spell it out, it's going to really help your graph. Okay? How about what's happening at x equals -2?
That weird thingy.
Well, before we get to -2, we're concave up. And after we leave -2, we're concave down. So at -2, we've got an inflection point. Same thing at 2. Okay? So you've got to have inflection points at those two locales. Okay? These two are statements about the what term behavior of the graph?
And behavior.
The end behavior or the long-term behavior of the graph, right? So I know that in the long run, as I go to the left, I need to have a horizontal asymptote at y equals -2. And in the long run, as I go to the right, I need to have a horizontal asymptote at y equals 0. Okay? Remember, you can cross horizontal asymptotes. That's no problem. All right, so keep working on it. See what you can do. Anyone think they've got it? You come take a look. Yeah. So, let's see. So not quite. So remember, we said we wanted to have a local max at 1. So not quite there. So not a 0 at 1, but a local max. Likewise, we don't have a 0 at negative. Well, you do have an inflection point there. But let's see. You've got a concave. So it's going to be concave up before we get there, and then down after we leave. So let's check that. Almost. It looks like you actually got an inflection point right here. You see that? So it's so right here it's concave up, but right here it's concave down, right? So you put an inflection point right there as opposed to. So it should keep going up in that manner until it gets -2. So sweep it up, and then sweep it down, and sweep it up again. Try that and try to get the maximum at 1. Yeah. That's it. One person's got. These are tough, folks. These are tough.
So we know this is because
Just try to emphasize that just a little bit more. That's okay. So let's see here. We've got to, we're coming, our indicators towards here, and we've got to be increasing. We increase always until we get here, right? One, increasing. And we're doing so for a while in a concave up manner. Like a sweep like that. Yes, so it's concave up, and then it's concave down.
it's just stating the fact.
Not the one you just passed out.
There's a local max at that point. So just put it
Oh, he does?
That's all right. These are really tough, folks.
I'm just saying, do you have an extra form for 3?
No, I don't.
See, now I'm embarrassed.
That's pretty doggone close. Except you need to have a maximum at 1, so you need to keep going up a little higher and then come down. There's no cusp there at +2. All right, folks, here it is. Do keep working on these. I think I put 3 on your review. Okay, so you get 3 more tries on them. Okay, let's put it all together. This does take some work. I think identifying the maxes and inflection points are helpful. So I'm going to put a max at x equals 1. Let's go ahead and put something there. Here's 1. So let's put a maximum up there. Okay. If I don't like where that is, I'll change it. Okay, but I'll start with it there. Then I've got an inflection point at -2. So let's put it down here. And I've got an inflection point at -2. So I don't know. Let's put it right here. Okay. So I put on those inflection points in the max. Okay. Now, my long-term behavior says way out this way, I'm close to -2. As I'm coming in towards the field of the graph, I'm increasing until I get to 1. And before I get to -2, I'm increasing in a what manner? Concave up. So how do you increase? Show yourself a parabola. That's concave up. Where is that also increasing? This part right here. So until I get to -2, it should be making that shape. You see that shape? The increasing concave up. Yes?
Is that first point 1 or -2? -1?
Oh, it sort of looks like, by my scale, it sort of looks like it's at -1. It's not. It's at -2, but I've got a pretty lousy scale. How about that?
Okay.
Yeah. So that's increasing in a concave up manner. After I leave -2, I'm going to continue to be increasing, but now in a, my second derivative is negative, so that's telling me I'm concave down. So I'm going to keep increasing in a concave down manner. Show me concave down. Where on that concave down shape are we also increasing? So it should look something like this. At 1, I've got a local maximum. Then beyond 1, I'm going to start decreasing. And I'm going to keep decreasing in a concave down manner. Show me concave down. Where is that decreasing? So just draw a generic shape like that. After -2, though, after +2, I'm going to continue decreasing, but now in a concave up manner. Show me concave up. Where's concave up decreasing? So it's going to look like this. Okay. Now there are other ways you could have done this. Notice none of these problems have anything to do with actually what the y values are, but you do need this maximum to be above the points around it.
There's an inflection point at x equals 2 and an x equals -2 is what that b means, right?
That's part of what B's telling us. Yeah,
Wait,
and
no.
it takes practice to see that.
But you picked arbitrary y values for it.
I did pick arbitrary y values for all these, except that based on how this works, the local max is also a global max. But if you didn't realize that initially, that's fine. Just pick it and then try to draw it and then correct. But I think it was you did need to, I think, identify that x
saying
equals
1
1 is a local max, x equals -2 and +2 are inflection points. Now, could I have put the inflection point, I said the y value doesn't matter, but could I have put the inflection point down here? No, because eventually I've got to get towards this horizontal asymptote. If I put the point down here, I would have to be increasing to get to the horizontal asymptote, and I said I couldn't be. So I think basically any answer to this is going to look similar, but there's likely more than one graph, but I don't know.
And you said, is 1 also your global max?
In this case, it is. I don't think there's anything that at first light would indicate that, except that it was always decreasing from -infinity to 1, and then, excuse me, always increasing from -infinity to 1, and then always decreasing from 1 to infinity. So I think that's probably strong enough to say that you have a global max there. That is. Yeah. Yes?
Yes.
So based on this, are we able to get an idea of what the first derivative and the second derivative look like? I'm just curious, like the graph.
Oh, that would be hard. I didn't think of asking you that. Certainly.
I'm just trying to
So,
finish picturing it.
well,
I mean, it's okay.
let's see what we can do. So the first derivative, the function would be positive until we get to -1, and then it'll be negative, right?
So you get to -1 on this side, right?
Sorry, +1.
Okay.
Yeah, I'm getting my left-right orientation all messed up. I was supposed to drive to Boulder Canyon campus today, and I walked to work.
Nice.
We got to the parking lot and realized I didn't have a car. So the second derivative here is positive, which means the function should be, excuse me, its derivative, sorry. The second derivative is positive, which tells us the first derivative has to be increasing before we get to -2, decreasing here. So I think we would have something like this. So here's -2, here's 2, here's -2. So we've got to be increasing. No, increasing and positive. So something like this, increasing and positive until we get to 2, -2. Then we start decreasing until we get to here, keep decreasing until we get to here, and then we start increasing. I think that's what the first derivative would look like. Okay. It's a pretty hard one to do. Yeah. But that, I think that would be the first derivative of that. Okay, let's keep going, folks. The next thing I want to talk about is what's called the second derivative test. Okay, this isn't going to necessarily give us more information. It just gives us a different way of finding the same information. Sometimes this test is faster. Sometimes it's the best way to go. It just sort of depends on the problem. So our second derivative test says this: suppose f double prime is continuous on some open interval containing c, with f prime of c equal to 0. Okay. Then if f double prime of c is less than 0, f has a local what? Well, let's see here. We've got a horizontal tangent line, and we are concave what? Down. If we've got a horizontal tangent line and we're concave down, show me concave down. Where on a concave down do we have a horizontal tangent line? At a local max. So if we've got a horizontal tangent line and we're concave down, then we've got a local max. Now careful, that requires that f double prime exists, right? And be continuous. Okay. What about if f double prime is positive? Well, if f double prime is positive around c, then the function's what? Well, that would be the final answer, but it's if f double prime is positive, then the function is concave up. If we also have a horizontal tangent line, where on your generic concave up shape do you have a horizontal tangent line? At the local min. So f has a local min at x equals c. This test is not as, I guess you'd say, robust as the first derivative test, because it has a third case in which it's inconclusive. If f double prime of c equals 0, the test is inconclusive. Generally, what that would mean is you should look at your first derivative test then. Okay. So here I've got a function. Okay, it's a fairly complicated one. This is my first example of doing a complicated one. And folks, in the interest of time in class, I did the hard work. I gave you the first and second derivatives in factored form. Okay? That could be, for some of you, up to half an hour's worth of work. Okay? You want to work on that to the point where it only takes you 10 minutes to take those derivatives and put them into factored form like that. Okay? So you do need to practice getting competent at calculating those derivatives and then putting them into a single fraction form. Okay? You'll get plenty of examples into my math lab. Okay? But you do want to sort of push yourself. I would hit the similar exercise button several times on these questions to get a little bit faster at them so it doesn't bog you down when you have to do it on an exam question. Okay? All right. So we're looking for all extrema here. Okay? We're looking for all extrema. So let's go ahead and find our critical numbers. Okay? Well, what are our critical numbers for the first derivative? X equals 3 and x equals 5. Why is 3 up there?
Because x equals here, that's where you have a 0.
That's where you have a 0 for the first derivative. Somebody else, why is 5 up there? So that's where the first derivative is undefined. Okay? What about the critical numbers for f double prime? That happens at x equals 5 and at x equals 9. Now, what are we going to do with the critical number at x equals 9? I'm not going to do anything with it. How come? It's not in the it's not in the interval that we're considering, right? So be careful with that. This is where I'm saying there's sometimes a lot more going on with these questions than we see in just the polynomial cases. Okay? So we're not going to consider that one.
It's the same with x equals 3 for the first derivative.
Oh,
Oh, snap. Got it.
yeah. So Kevin brings a really good point. So last semester this was a critical number. This semester it is no longer a critical number. I'm going to go ahead and keep it there because it's a point of interest. How about that? Oh, no, 3 shouldn't be. No, we're not going to consider 3 at all. Sorry. No. The question was whether endpoints would be considered critical numbers, but that's not an endpoint. So it is clearly outside of the interval, so we are not going to consider it at all. Yeah, I'm sorry about that. That was a mistake. Yeah. Okay. So we're not going to consider 3 at all because it's outside of there. Okay. So what should we do? Well, let's go ahead and let's determine if x equals 5 is a local max, min, or max or min. Or undetermined. Okay, so this is a little bit strange to be doing as our first example, but I think you guys can follow. I would like to go ahead and do the second derivative test on this. Why? Because I've already got the second derivative. Okay? But if I plug 5 into the second derivative, I get that it's undefined there too. So the test is inconclusive. Okay, so what test will I have to do on this one? Let's go ahead and just do the first derivative test. So let's make our number line. Let's put all the interesting points on here. Why do I just... That seems silly. Let's make this a... folks, let's make this a -4. Right here. Sorry about that. Okay, so in that case, we will go ahead and keep 3. And not exclude it. I'm sorry to change that on you folks. So we're gonna consider this the interval from -4 to 6, and we're gonna go ahead and then we would allow 3 because 3 is definitely in that interval. Okay. So let's go ahead and put all of our critical numbers on here. We've got a critical number at 3 and a critical number at 5. We're going to go ahead and take our test points. Let's take a test point, I don't know, how about 0 will work. And we'll take a test point at 4, that'll work. And let's take a test point 6. We really shouldn't take something that's an endpoint, so let's take 5.5. Okay. Let's look at f prime of the test point. Okay. If I plug in 0 into the first derivative, let's see here. The numerator is 0. Excuse me, the numerator is negative. What's the sign on the denominator? Now, for the third, we're going to be taking a cube root, that return a negative, but then what do? It's a 2. We square it. So the denominator, in fact, in both cases, we notice the denominator will always be positive. So really, it just matters the sign on the numerator. So we get negative, so we're decreasing. What about if we plug in 4? We still get negative, so we're decreasing. What if we plug in 5.5? Then the numerator is positive, and the denominator was always positive, so we're increasing. Let me double check that, folks. Sorry, when I plug in 4...
You'd be increasing there.
Sorry, folks. When we plug in 4, we get positive, so we're increasing. When we plug in 5.5, we get positive, so we're increasing. Sorry about that. Okay. And let's go ahead and plug it into the second derivative. If you plug in 0 into the second derivative, we are negative, so we're concave what? So we're negative, so we are concave down. That doesn't seem right. Put a should have a negative sign in front of it. So we're concave down. If we plug in 4, folks. I was tinkering with this before class. I should have left all alone. Let's return to this example next time. I think one thing that happened, I think I miscopied the second derivative. Sorry about that. Okay. I think what I'd like to do, folks, we're going to return to this next time. I'll do a few more examples of this, but I do want to get started on the L'Hopital's rule so you can see that. So I just handed out some notes for L'Hopital's rule.